faster. So, last class we have seen that how to solve the what is called optimization problem using the KKT condition, necessary and sufficient conditions, and we also seen that there is a inequality constant is there and equality constants are there. If inequality constants that x of k is less than 0 for j is equal to 1 to n, that is 1 to small p m j, if this constant this 0 is part up with a small positive numbers, agree, then and also the equality constants is this is right hand side is part up with some positive number, agree, I is equal to 1 2, there are such p equality constant, then what is the effect of objective function value of this, we have studied it. In other words, we have studied the sensitivity analysis after what is called post analysis, we have studied it, and also we have studied the effect of cost function scaling on the Lagrangian multiplier, effect of cost function scaling on the Lagrangian multiplier, and also we have studied the what is the effect of scaling on constants, that constant these are the constant, if you what is the effect of scaling if you multiply it by this p I and h I is multiplied by m p I and g I g j of x inequality constant multiplied by m I, then what is its effect on the Lagrangian multipliers, that we have studied it. So, today I will start in what is called convex set and convex function. So, what is convex set? A set is a convex. Suppose this is the set, this set will be convex if any point on this set, if you take any point on this set, this is the set S, the set S is a convex set. If we take any point on this set, agree, any point on this and form a line segment, agree, then this any point on the line segment belongs to that set, then we will call this is a convex set. So, what we can write, a set S is convex if the line segment between 2 points, any 2 points, between any 2 points lying in any 2 points in S in that set, agree, lies the line segment between any 2 points in S lies in that set in S, then we will call that set is a convex set. So, let us call we have a this set is there. We form a line segment by joining the point P 1 and P 2. Okay. So, these 2 points that P 1 and P 2 we join. Any point on this line segment belongs to that, if there that set is there in that set, then we will call the set is convex set. Agree? So, in convex set we can always write it, let us call x is a any point here, this P is a point whose vector is x 1, this is a vector of x 2, agree, these 2 points, then linear combination of theta, or you can say that alpha into x 1 minus alpha into x 2 belongs to that set. So, if you consider it is a single variable case after this x 1 and x 2, there are 2 points are there, you join with these 2 points, agree, then any points on this line, any points on the line, if it belongs to that set, that is what is called S set. It can be in n dimensional variables x 1 x 2. So, only the condition is if you consider this is alpha 1 and this is the alpha 2. So, alpha 1 plus alpha 2 must be equal to 1. Then when alpha 1 is, let us call here, when alpha is 0, when alpha is 0 is nothing but a x 2 point, this point, when alpha is 1 is nothing but a x 1 point. So, any point alpha value, any point between 0 to the alpha value is less than equal to greater than equal to 0. So, any point alpha between 0 to 1 indicates the corresponding point on the line. If all the points on the line belongs to that set, then this will be called as a convex set. So, we can see this one by, let us call, we have a simple octagon, regular octagon. One, two, three, 4, 1, 2, 3, 4, 5. Okay. This is I am drawing octagon like this way. This is the circle. Agree? So, this 3, 4, 5, 6, 7, 8. So, these are the octagon. So, if this octagon belongs to a set S, let us call this belongs to the set S, any point on this line, any point on this octagon, if we join together, let us call P 1 and this is a P 2, this point is P 2. Any point on this line, 2 points x 1 and x 2 or P 1 point P 2 we join together, and any on this line segment any point belongs to that set, then it is a convex set. So, the octagon of this nature is a convex, this is the convex set. So, let us call this is another set is like this way. This belongs to this is a set S set, but in this case any point on this set does not belongs to that set. You see, any point this is P 1, this is P 2. If you make a line segment like this way, agree, and the any points on this segment, this point, these points are not belongs to that set. So, this is not a convex set. This is not a convex set. What we will call non-convex set. So, in this set, this is the point, this is the point. If you join these 2 points, thinking just considering as a chord, we have joined it. So, any point on this line does not belong to that set. So, this is not a convex set, it is a non-convex set. So, geometrically, if you have a set is there, you just join 2 points agree in that set and you will form a chord. If all the points on the chord belongs to that set, then it is a convex set. In geometrically you can say chord between 2 points you joined a line or line segment. If any points on this line segment belongs to that set, then it is a convex set. Next is convex function. And convex set, this condition must be satisfied, any point x 1 and x 2, and it is a alpha 1 is 1 minus alpha, the alpha 1 plus alpha 2 must be equal to 0 or equal to 1. So, if you have a this you can write it. Now, a convex function, a function is said to be a function in general of n dimensional, a function of n dimensional variable, n variables. So, let us call this function is f of x n cross 1 variable defined, that function is defined on a convex set, agree, that function is defined on a convex set, the function is defined, variable defined on a convex set. S is said to be convex function, is said to be convex function, is said to be a convex function if and only if necessary and sufficient condition for any 2 point any two points x 1 whose dimension you can say n cross 1 and x 2, any 2 points on that set and x, and set is your S. On that dimension of this is x 2 dimension n cross 1 this, and there is a scalar quantity theta is greater than equal to this, or let us call, since I have used alpha, use alpha is greater than this, then one can write it this one f of alpha into x 1 plus 1 minus alpha into x 2 equal to less than equal to f alpha less than equal to alpha into f of x 1 plus 1 minus alpha f of x 2. If this condition is satisfied, then we will call the function is a convex function in the convex set. This condition is satisfied. One can easily see this one by a single variable case, and that can be extended for a n variable function case. So, what is the definition of convex function? A convex function n, a function of n variable is said to be convex function if it in a set as if and only if this condition is satisfied, and where that our, if you consider the alpha is, let us call alpha 1, this you consider is a alpha 2, then alpha 1 plus alpha 2 is equal to 1. Okay. So, 2 points that now see this one, this 2 point, when alpha is 0, it indicates the x 2 points in n dimensional vector x 2 point. When alpha is 1, it indicates the x 1 point in n dimensional vectors. Alpha in between 0 to 1, any value that indicates the any value on this vector, that x 1 and x 2 within this with these 2 points, that vector what will generate, it indicates any point on that vectors for any values of alpha from 0 to greater than 0 to 1. So, if this condition is satisfied, then we will call the function is a convex function in that convex set. So, let us see with an example of this one. This, that is, if this is a this condition is there, then the function will be said to be a convex function. Okay. And it is a strictly convex function when this condition is satisfied, alpha into x 1 1 minus alpha into x 2, this is less than equal to, not equal to, less than equal to, previously it is a less than convex function. Now, I am telling it is a strictly convex if this function value is less than equal to alpha into f of x 1 1 minus alpha into f of x 2 values. So, what is this? Just say for a single variable case, what is the meaning of that one? So, suppose this is the function f of x. Now, you consider this is a single variable case, x is a one variable. So, single variable, this is f of x, this is the function plot. So, we take a 2 points here, let us call P is the point whose coordinates are, let us call x axis x 1, this is P 2 is there, 2 points on the line on the curve function is x 2. So, I told you that with these 2 points draw a straight line, which is nothing but a chord, you can say it is a chord. So, this indicates, you see, if it is a function is convex according to the definition, that any point on this line between x 1 and x 2, any point I can express like this way, any point on this line, let us call x, any point from x 1 to x 2, any point x is equal to, I can write alpha into x 1 plus 1 minus alpha into x 2, agree, or alpha values is greater than less than equal to 1, greater than equal to 0. So, any value of alpha from between this range, the x will lies anywhere between the x 1 and x 2. See clearly, when alpha is 0 is nothing but a x 2 point. When alpha is the extreme limit, when alpha is 1 is nothing but a x 1 point. So, alpha value in between this range, it lies between x 1 and x 2. So, the any value between x 1 and x 2, the function value is that one, and what is this value x, any value in between x 1 and x 2 is that one, that expression. So, what is the function value? F alpha into x 1 plus 1 minus alpha into x 2, this value, this coordinate, this is the coordinate of that one, that x, if you consider this is x, then this is the coordinate of, you can say x, and y direction is that one, that is the function of alpha into x 1, 1 minus alpha into x 2, this value, okay. And this value always less than any point corresponding x, what is the value, what is the value on the chord, value of this equation value on the chord, this. So, this quantity always greater than this quantity, definitely. Now, how will you find out this quantity? That is simple geometrical configuration, one can find out the equation of the straight line. Once you know the equation of the straight line, that any point x, what is the ordinate of this one, you can find out, which in turn it can be expressed like this way, this quantity is less than equal to, you see when it will be equal to, at the extreme points of the chord, the function value and the chord value at the extreme point of p 1 and p 2 both are same, that is why equal to sign. Other than this point, these 2 points, this chord, any point on the chord, okay, function value y, function value, that will be always greater than the function value of f of x. You see any point here, this function value, whatever the function value is there, at the chord value at this point is greater than this one. Equation of this one, if you know, because I know the equation. How will you know the equation? You know the ordinate of that one, change in ordinate and change in x. So, slope you can find out. Once you know slope and it is a function of x, in order to find out the y, this function equation, agree. So, we can write it this one always alpha into x of 1 plus 1 minus alpha x of 2, that is f of x of 2. How will you get this one? This point value, how will you get? I told you, find out the equation, that what is the equation of this straight line, agree. Then you can, you find the equation of this straight line, then you find out the what value of x, what is the ordinate of this one. So, that you can find out, and after simplifying this one, you will get this one. So, if this condition is satisfied, it indicates that function is convex function and belongs to the inconvex set, that is this. One can easily verify that one by the finding out the equation of this straight line or chord equation between point 1 and point 2, and find out the value of this function value of this chord value, that this equation value at x is equal to x 1 is nothing but that one after simplifying. So, this is our convex. What is the definition of concave function? Definition of concave function is similar way one can find out the similar way one can find out that the 2 points are there, let us call this is the function f of x, that let us call single variable case we are explaining, then we can extend for n dimensional case. So, this point is p 1 and this point is P2, P2, this is P1. Draw a chord between these 2 points. Agree? This is x1 and this is x2. Agree? Now, you can find out that linear combination of these 2 points, agree, any points on this line between x1 and x2, any points, this one I can express like this way, x is equal to alpha into x1 plus 1 minus alpha into x2, and this is the definition of our convex set. If you recollect that what we have discussed, the convex set is belongs to in the convex, x is belongs to this our convex set, this one with this expression, and this one alpha varies from 1 to 0. Once again, when alpha is 0, this is x2, when alpha is 1, it is x1. So, any point on this line, any point on this between the 2 points, I can take the alpha values in this range, greater than 0, less than 1. So, let us call what is the function value. You see in this case, function value at any point between x1 and x2, let us call x, is always greater than the what is the value of this on the chord, what is the value of this equation of this straight line, agree, what is the y value at this point, it is always less than the function value f of x function value. So, one can write it for convex function in a convex set, I can write it alpha into x1, same expression 1 minus alpha into x2, what will be this is the function value at this point, it is greater than equal to this point function value, this function value, and this is the this quantity is that one, and this quantity I am writing alpha into f of x1 plus 1 minus alpha into f of x2, this one. So, convex function, if this condition is satisfied, agree, then I will call the function is concave function in the convex set, agree. This one, this you see from graphically also, this nature of the curve is concave curve, provided this condition is satisfied. This means that x belongs to any convex set, agree, and if this condition is satisfied, that function is a convex function. And how one can do it in the similar manner I can do it. Suppose f is a function, I will define if f is a function which is a, let us call, concave function, I multiplied by, let us call, g is equal to minus f. So, this function g function will be a convex function. If it is a convex, multiplied by f minus, it is a convex function, and I know how to, if I can check the g is a convex function in the set S. In other words, I can say f is a concave function in the set S, agree, just multiplying f by S. So, our definition then convex function is that we can write it, the definition for concave function, definition of concave function. So, these are the chord, in the beginning also we told this is the chord joining these 2 points, agree. So, definition of convex function, a function f of n variables defined on a convex set S. If it is defined on a convex set S, then any point on the set I can express, any point on this set X, I can express alpha into x 1 2 points, if you know 1 minus alpha into x 1 x 2. and that x 2 if belongs to that set, then it is a convex set. In the set S is said to be a concave if the function that our f, if the function f is multiplied by f minus 1, that g agree, is convex. If minus f is a convex, then I will tell f is our concave function on that belongs to that set, convex set. Agree? So, this next is remark, let us see remark. A linear function is a convex as well as concave functions. Just see, a linear function is convex as well as concave function. Any linear function I can treat as a convex or concave functions. Let us call this is again it is a single variable case. If you see what this is our linear equation that belongs to in a convex set. Now, whether it is a convex function or not or concave function or not, you see take 2 points on this set, let us call P 1 and P 2, join these 2 points, and it is just the same line as the original straight lines. So, naturally it may be a convex as well as concave function, okay? Because equality sign is now it is just valid equality sign only, both cases. So, you want just remember a linear function, it can be a convex function or concave function. I can say both this one. Next is the properties of that what is called convex functions. Some properties we will just discuss before we discuss the optimization problem using the what is called convex optimization problems. So, the properties convexity properties, convexity properties. So, one thing is if S is a convex set, if S is a convex set, S is our convex set, agree, and alpha belongs to our real positive quantity, agree, alpha is any positive real quantity, then S is our set which is a convex set. This is a convex set, this S is a convex set, agree. Then if you multiply by this convex set by alpha, this also a convex set. What I am telling, if your S is a convex set, if you multiply by that set, either you enlarge or you just attenuated this by alpha, alpha may be greater than 1, less than 1, agree, but positive quantity. If it is so, this one, then alpha into S is also convex set. That means, if your alpha is greater than 1, the set is enlarged. If alpha is less than this one, set is contracted, agree. So, this is one property. What is this property? If S is a convex set and alpha belongs to that R plus 1, then alpha into S is convex set. This is one. Another property is there, if there are two convex set is there, agree, intersection of two convex set is also a convex set. we have a two sets are there, S1 and S2 are the two convex set. Agree? Intersection of these two convex set is also a convex set, but union of two convex set is not a convex set, it is a non-convex set. So, we will write it this intersection of convex sets is convex set. The two sets are there, let us call S1 and S2. The two sets intersects, which one is the intersection of this, which one common set is there that belongs to a that convex set. That union of two or more convex set, the union of two or more convex set is usually non-convex set. That means, we have a S1 is a convex set, S2 is convex union of this one, let us call this is a convex set and this is a convex set something. Then you see this is the union of this one, it is not necessarily a convex set, because if you take a one point P1 is here, P2 is here, P2 is there, join these 2 points, any points on the line of this one must lie in the convex set, but it is these points are not belongs to that convex set. So, this is not a union of two or more convex set is not usually not a convex set, whereas the intersection of two convex set, the intersection of two convex set, this one belongs to a that our convex set. So, this third point is this one. Now, if f is a convex function, agree, f is a convex function, if you multiply it by f by a scalar quantity which is greater than positive quantity, which is positive quantity, then resultant is a convex function in that convex set. Agree? So, another property is that if you have a two convex functions are there, two convex function f1 and f2, two convex function there, sum of these two convex function is also is a convex function. So, last two properties is like this way, if f1 is a convex function, if you multiply it by some real positive number, this f1, the resultant is a convex function in that convex set. So, our fourth point is, if f is a convex function and alpha is a real positive number, then alpha into f of x is a convex function. In that set. Then fifth property is, if just now we mentioned if f1 and f2 are convex functions on the set S, okay, then f1 plus f2 is also a convex function on S. This proof you can do simple by the definition of our convex function, that our definition of convex function, from that one the 4 and 5 you can easily verify this one, agree. So, if f is a function of convex function, I multiply it by scalar positive quantity, agree. So, that function also belongs to that convex set. Now, you write it because f1 and f2 are two convex function on that set. So, you take any 2 points on that set, write what is the condition for F1 to be a convex set, right? What is the condition for F2 to be a convex set? Then add to these two things, and resultant you see whether you will be able to express in this form. If you can express this form, then it is a convex function of that one, that can be easily proved. So, these properties are useful in studying the what is called constraint problems, constraint optimization problems. So, these properties are very useful, useful in the study of constraint optimization problems. Problem. So, this. So, let us see some of the facts of convex optimization convex functions. Agree? So, let us call f is a function, agree, and belongs to C 2. This indicates C 2 means it is C continuously twice differentiable. Function is continuously 2 means twice differentiable. If I write 3, it is a 3 times continuously differentiable, this function. So, this is the function f of x is continuously twice differentiable. See, continuously power 2 means twice differentiable. If this, then f of x is convex function over a convex set S. F of S is a convex function over a convex set S containing an interior point agree. So, we have a f of function is there belongs to that set, the f of function belongs to that set, and there is a interior point, one point in the set, interior point. If only, if and only if this function is a convex function, if and only convex function over the set S, agree, and containing a interior point, one interior point, if and only if the Hessian matrix H of f is a function, we know in our earlier lecture how to find out the Hessian matrix, that means second partial differentiation of f with respect to x, the Hessian matrix. If and only if the Hessian matrix is positive semi definite, is positive semi definite through out S set, meaning convex set. In the convex set, any point on the convex set, if the Hessian matrix of f, means second partial derivative of the function f, this is the Hessian matrix for over the all points of this set, if it is a positive semi definite matrix or positive definite matrix, then I will call the function is a convex function. Agree? This is the in this. So, let us see this proof of that one. That means, once again I repeat that one. Suppose if you have a function f of x and which is belongs to C 2 means continuously twice differentiable, then function is called convex function over the convex set S containing the interior point, containing an interior point, if and only if the function if you do the second derivative that twice if you differentiate this one the function with respect to x, which is a Hessian matrix, and this Hessian matrix is positive semi definite over the convex set, then we will call the function is a convex functions, or this Hessian matrix is positive definite matrix, also it will be carrying the convex function of this proof. So, let us call we are, since we are considering that there is a interior point is there in the set of this one, let us consider by Taylor series expansion now. By Taylor's theorem, we have, suppose we have f of y. F of y, I am writing y is there is a interior point around this interior point there is a y, x is interior point around this one is y. So, I am writing y, I am writing as if it is x, this is a delta x, agree. Now, this equal to by Taylor series expansion I can write nearly equal to f of x plus gradient of this function transpose of f of x at this one, agree, multiplied by incremental change y of x means delta x plus the second terms in the Taylor, third terms in the Taylor series or second order terms of this one is half that y means delta, this is a delta x transpose into that Hessian matrix of f of x, agree, multiplied by y minus x. Whether x is a vector or scalar, this is true this one. So, it is nearly equal to this one. So, f of y, if you bring this part in that side left hand side, f of y minus this part is equal to this quantity, and this quantity will be positive, right hand side will be positive or negative depending upon the value of the Hessian matrix over the that our set S. If we can say that Hessian matrix value over the set S is a positive semi definite matrix, it indicates this quantity is a positive semi definite, this quantity. That means that that this quantity is positive semi definite, means this value of this one either it will be 0 or it will be greater than 0, this one. So, now this I can write it now, if you just see this one f of y minus f of x plus gradient of this f of x into y minus x, this quantity is equal to nearly equal to, I can write it half y minus x transpose, and I am writing the gradient of that one. Agree? And gradient of this one, let us call x, that is not that is Hessian matrix of this one H into y of x. So, now this side value, right hand side value will be positive or 0 when this matrix value over the set S, if it is a positive or 0. When it will be this, Hessian matrix should be positive semi definite. What does it mean? This indicates that this is positive, means this indicate f of y is greater than this quantity. Agree? So, let us see what is this meaning of this one, f of y is greater than this quantity, what is this means. So, I can write it is clearly I can write from the equation that, or this x for any value of x in this, because I told you this is our x and this is our y. Any point in this I can write it alpha into x plus 1 minus alpha into y. any point on this one, any point, any 2 points in this line. So, I can write it this alpha into this, if you can write it this, the y plus y, that it is this one I can write alpha into x minus y. Just see this one, in the x is this point, y is this point, I multiplied by this one some positive component alpha, means since these 2 points belongs to that set S, any point joining these 2 points, this chord, any point on this line belongs to that set, means it implies that one. So, y is that one, then alpha into x minus alpha into y, that one, agree this point. So, I can write in place of anything here point of this one, x will be now replaced by that quantity, you can replace by that quantity, any point on this curve, on this set I can replace. So, this positive indicates, this one positive indicates that this Hessian matrix, this matrix should be either positive or 0, when this Hessian matrix will be positive semi definite matrix. So, this indicates that f of y, this indicates that f of y, clearly this indicates that f of y will be greater than equal to f of x minus plus gradient transpose of f of x into y minus x, this indicates. Geometrically one can say, because this is the condition, if you see I am writing the f of x is twice differentiable continuous, the function is continuous, the function is convex function over the set containing an interior point x, if and only Hessian matrix of S is positive semi definite matrix. So, what is this one? If you see for a scalar variable case x, and we have a this type of functions is there. So, this is our f of x, this is f of x, and y is a some point is here y, this is f of y, this is y, and any point in this range we can express by a convex set definition is alpha into x plus 1 minus alpha into y is equal to any point on this, you can write it. Let us call any point on this one is x bar, I can write x bar this one. Okay. So, now see this one, what is this meaning of that one? F of y, a function value is that quantity, is always greater than, what is the function value is here, plus this quantity, and what is this? This is the gradient at this point. For scalar case it is nothing but a slope at this point, okay, multiplied by change in this one, that means this multiplied this slope multiplied by this, what you will get it, that quantity, this is the your y minus x, agree. So, y minus x, and this is the slope of that one, slope means this quantity divided by this quantity, that slope is given, multiplied by this, if you know the slope multiplied by this, you will get it this quantity. So, f x minus of this quantity means this quantity indicates this is f of x plus delta f of transpose y minus x, this is always get a less than equal to, this is always less than equal to that one. Okay. So, therefore, if clearly we can say clearly, if the Hessian matrix H of the function f of x is positive semi definite everywhere, positive semi definite everywhere, then function then f of x is a convex function everywhere, then f of x is a convex function. So, this is that, and that is a important theorem is this one, that one, because this is a convex optimization problem, this theorem is most important one. That theorem is, let f of x whose dimension is n cross 1 be convex function defined, this function is defined over a convex set, this function convex function defined over a convex set S belongs to that else in n dimensional case, then the local minimum is the global minimum, then the local minimum provided the function is convex function, mind it, if the function is convex function over the convex set S, then local minimum of this function will give you the global minimum of this function. Local minimum of the function, local minimum is global minimum of f x over the set S. So, what is the proof is very simple. If you say, let us call x star, now x star which is n cross 1 be a local point, be a point of local minimum. This is the local minimum point, local minimum. Agree? That means you have this, that at this point is local minimum, we got it x star. Agree? So, we can write it now, f of x star is equal to less than equal to, if you take any point around this, let us call x. So, f of x, and since it is the local minimum point, f of x is less than equal to x star plus x minus x star. This is, you can say, delta x, okay, x, this is the delta x, you can say. So, it is less than this is equal to our f of x, this is x. So, you can write it, there is a, let us call there is an any, now these 2 points are there and these 2 points belongs to a convex set. Any point on this line, I can write it this one f of x bar, this by definition of this one, I can write it this equal to, what is x bar? Let us call this point is x bar, okay, this point is x bar. So, I can write it this x bar is equal to that x alpha into x star plus 1 minus alpha into x is x bar, where alpha greater than 1 less than equal to 0. This you can write it. Now, this we can write it by definition of convex function, because it is a convex function definition, we can write it that alpha into f star of x plus 1 minus alpha into that what is called f of x. We can write it that one, okay, since f x is a convex function, that one. So, this we can write it, since x bar, this is the x star is a optimal point, minimum point, x bar other than this. So, I can, if I write it in place of x star, if I write it x bar, this quantity x bar is greater than x star function below, because the x star is a optimal point plus 1 minus alpha f of x. So, if you take it, this is that side, this quantity that side, this implies, after taking this side, this implied f of x bar is less than equal to f of x, this, agree, this we have shown. So, this implies, and we know f of x star is also less than equal to f of x. So, since if you say since f of x, since x is any arbitrary point, x is any arbitrary point, hence f star of x is less than of f x. See this one x that is what we x is any arbitrary point. This may be here also this side, because it is belongs to that set now. So, this we can write it for all x belongs to that set. So, our conclusion is that x star is a point of the global minimum. Okay, because these 2 points I have taken it this one, these 2 points belongs to that convex set, and x may be any arbitrary any point, and since f x bar is less than f x, agree, and we have shown it that f star is less than this one, it indicates the f star of x is less than any point on the global, means in the set itself, always this f star is less than that one. So, it is a global minimum. So, our conclusion is if f x is a convex function over a set S, agree, and that minimum point, that means local minimum is nothing but a global minimum of the function if f of x is a convex function, then only, and over the convex set. So, next class we will just discuss other points. Okay. We will stop it here now.